Hello, algebra students. Mr. Lawrence here, and I'm feeling a little bit hoarse, so I apologize. I'll try to speak up as best I can. Anyway, we're talking more about number systems, and particularly about rational and irrational numbers. Now, right off the bat, I'd like to define rational numbers. A rational number is any number that can be written as the quotient of two integers. Okay? If it's rational, you can write it like a fraction using integers. Okay? Rational numbers include all the natural numbers 1, 2, 3, 4, 5, 6, 7, 8, 9 on forever. They include all the whole numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 on forever. They include all decimals that end or repeat, like 3.86 repeating, okay, or 3.4 repeating. They include decimals that end, like 7 1/4, 7 25 hundredths. Okay, they include mixed numbers, etc. Assuming the decimal part is a decimal that repeats or terminates. Now, irrational numbers are numbers that cannot be expressed as a simple fraction using integers. Okay? So let's take a look at these numbers here. And let's see if we can break them up into rational and irrational. Well, 0 is pretty obvious. It's a whole number, and therefore it's rational. Can I write 0 as a fraction? I hope you know this. A lot of kids don't, especially 8th graders. Wouldn't that be the same as 0 over 5? You know, there were 5 pieces of pizza, and Sam didn't save me any. I got 0 of the 5. 0/5 is the same as 0. Okay. 1/2. That's 2 integers being divided. That's a fraction. Okay. That's a rational number. Excuse me. -3/7. There's 2 integers being divided. You can think about it as -3 divided by 7, or you can think about it as 3 divided by -7. Okay, but they're rational. 10 is rational. Okay. 3.86 and the 6 repeats. Rational because there's a repeating decimal. Okay. 3 14 hundredths. Rational because it's a decimal that terminates. The square root of 100. Well, what is the square root of 100? Well, it's 10. It's got to be here, right? Now, pi is probably the most famous of the irrational numbers. It starts off 3.141569, and it goes on forever and ever and ever without repeating. Some of the digits may repeat, but there's no pattern to the repetition. Okay? This 6.1443 ... This means it goes on forever without repeating. Therefore, it is irrational. The square root of 2. 2 is not a perfect square. There is no number times itself that equals 2. Therefore, square root of 2 is irrational. Other famous irrationals include the square root of 3, the square root of 5, the square root of 6, square root of 7, square root of 8, square root of 10, square root of 11, and so on, so on. Notice I'm skipping the perfect squares. If you're wondering, the perfect squares are 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 169. Oh, I skipped one, excuse me. I skipped the gross one, 144. That's gross. 169, 196, 225, 256, or 16, 17, 289, 18, 324, 19, 361, 20 squared is 400. Those are the first 20 perfect squares, not positive perfect squares. I guess I could have included 0 in there. All right. So there's rational and irrational numbers. All right. Now I want to show you what happens when you use operations on rational and irrational numbers. Not always fractions, but you know, I've got the square root of 9 times the square root of 9. You could say, hey, this is 3 times 3, and therefore 9. Well, that's interesting, isn't it? Look, you had the square root of 9, and you multiplied it by itself. And then you simplified that square root of 9 is 3, and square root of 9 is 3, and 3 times 3 is 9. I find it interesting that you ended up with 9 as an answer. I wonder if that's going to work over here. Let's take the square root of 4 and get 2, and the square root of 4 and get 2. And 2 times 2 is, I'll be darned, look at that, a 4. Huh. That's probably not a coincidence. Let's try it again. Let's do the square root of 36 times the square root of 36. Well, the square root of 36 is 6. Of course, I'm only talking the positive square root here. And square root of 36 is 6, and 6 times 6 is 36. Yeah, it's happening too many times to be a quinky-dink. All right, well, let's see, how is that going to work with an irrational number? Because I can't take the square root of 11. I don't know it. It's a decimal. I can approximate it, but there is no number times itself that is 11. But I'm here to tell you that this is the same as this. The square root of 11 times square root of 11 is the same as the square root of 11 times 11, which is the same as the square root of 121. Where did I get 121 from? Well, I multiplied 11 times 11. And the square root of 121 is a perfect square. Remember, I listed them up there before? Hopefully you wrote them down. So the square root of 121 is 11. I want you to pause the video and try this one on your own. In fact, I want you to try two. I want you to try the square root of 7 squared. And I also want you to try the square root of 19 times the square root of 19. Oh, let's do one more. Let's make it real hard. Let's try the square root of 341 times the square root of 341. Okay, try those three problems. Please do them. Don't unpause the video until you're done. And then come back and see what my answers are. All right. Here come my answers. Again, I'm assuming you've already tried them. I know the square root of 7 squared, quantity squared like that, means square root of 7 times the square root of 7. Well, that's the square root of 7 times 7, which is the square root of 49. Square root of 49 is 7, positive square root. Look at that. That's 7's match. Now, you guys are pretty smart. Right, Leanie? I bet you realize that square root of 19 times square root of 19 is simply 19. And I have no problem with you going right to that answer, but make sure you can explain why, right? This work right here shows me why. This is the why part, okay? Very, very important. Got to be able to explain it. Okay, so let's go over to Mr. Zabo on this one. Square root of 341 times square root of 341. I'll bet you he said 341. There you go. Piece of cake. Now, what's going to happen if we use other operations on irrational numbers? Let's try the square root of 11 plus the square root of 11. Hey, you know, this kind of looks like x plus x, doesn't it? You've got the same thing added to itself. And x plus x would be 2 x's. Do you think the square root of 11 plus 11 is 2 times the square root of 11? Yeah, it sure looks the same, doesn't it? Where x is the square root of 11. In fact, it is. If I take like 3 times the square root of 11 plus 5 times the square root of 11, how many square roots of 11 do I have? Well, I have 8 square roots of 11. See, there's 3 of them right there. There's 5 more. They behave just like the variables. They're not variables, but they behave just like the variables. I just think that's really cool because it's so simple. You take this irrational number and you can do math with it. It's kind of a crazy idea. I mean, if I had, 10 square roots of 7 minus 8 square roots of 7, well, I'd have 2 square roots of 7, wouldn't I? And similarly, if I had 5 times the square root of 3 plus 2 times the square root of 11, excuse me, I would be done with the problem because they're not like terms, because the square roots don't match. So I can't put those together. Yeah, that would be done. Ooh, pretty crazy. Yeah, the square roots of the irrational numbers behave just like variables. All right. Now, by the way, 2 times the square root of 11, that is an irrational number, isn't it? 2 times the square root of 11. So if I take the square root of 11, add it to itself, I get an irrational number. Okay? But when I take the square root of 11 minus the square root of 11, I get 0, don't I? Which is a rational number, as we said before. That's interesting. In this particular case, if I add the 2 square roots of 11, I get an irrational number. But if I subtract them, in this case, I get a rational number. What if I divide them? Well, what's 5 divided by 5? It's 1. What's fire truck divided by fire truck? It's 1. What's 0 divided by 0? No, not 1. This is undefined. Undefined. You are never, ever, ever, ever allowed to divide by 0. Did you get that? You are never, 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 never allowed to divide by 0. You never divide by 0. So, any non-zero number divided by itself is 1. But it doesn't work for 0. There is no definition in mathematics that lets you divide by 0. So the square root of 11 divided by square root of 11 is 1, which is a rational number. It's a rational number. Now, that's not always going to be true. These are just, these cases. I can check out other things where maybe I'll take the square root of 5 and I'll try to add the square root of 3 to it. Well, that's done. I can't do it because they're not like terms. Okay? If I do the square root of 5 minus the square root of 3, well, again, not like terms. I can't put them together. So I get the square root of 5 minus the square root of 3. Okay, now by the way, these are both irrational. Both answers are irrational. If I had the square root of 5 times the square root of 3, well, that would equal the square root of 15, right? But 15 is not a perfect square. Later on in the year, you'll learn how to simplify this a little bit. But for right now, we'll just leave it as the square root of 15. Actually, this won't simplify, but other products will. Square root of 15 is irrational. Okay? And then if you have the square root of 5 divided by the square root of 3, well, that's a weird one. You're going to have to learn how to rationalize the denominator. I'm not going to do it right now, but it's going to end up being the square root of 15 over 3, which is also going to be an irrational number. Okay, and I don't expect you for the test to know how to do this. Okay, I'm just telling you what that is right now. All right, that's going to be it for this video. Mr. Lawrence signing off. Have a good night, everybody.